All right, everybody, here we are in day 7 of math history. And what we're going to do is we're going to continue talking about the Greeks. We have probably, I think we might be able to finish the Greeks today, but we'll see. If not, definitely the next video we'll be finishing up the Greeks. So basically what we've been talking about so far with them is they're up here in Europe, and they're including this huge area. A lot of what we've done has been in Italy, so some of the people that we've been talking about, like Plato's Academy and stuff like that, it was part of ancient Greece, but it was actually in Italy. So that's where we've been so far. But we've noticed that here's the Mediterranean Sea, and just on the opposite side is where the Egyptians were, right? So what we're going to see today is we're going to talk about this town right here that's on the Mediterranean, and it's on the edge of the Nile, on the west side of the Nile. And that's one that was established by Greeks, but the Greeks are up here. So how did they get down here and establish this city called Alexandria? So that's what we're going to talk about today. So if you will, at the top of your map there, I've got an A. You can put whatever you want there for it, but know that that is representing a city. So now we have civilizations, we have some artifacts, and now we have a city to keep track of, as well as a few mathematicians running around. And this is Alexandria. It occurred sometime around 500 to 450 BC that the Greeks had a battle with the Persians. Okay. Now the Persians, typically that would be people who are living in like Babylonia. They're over more Middle Eastern kind of people. So whenever we're talking about them, now we're talking about the Greeks on one side, and we know that the Greeks had metal. We know that they had like city-states. So Athens was a very strong city-state with a very strong navy. And what ends up happening is they actually are very dominant in battle. So they end up going all over the place and kind of conquering. And so one of the things that they did was they went to Egypt, and depending on who you listen to, they liberated part of Egypt from the Persians. That's how this came about. And of course, it's right there on the Mediterranean, so it's relatively speaking close and easy to get to and those kinds of things. So what we've got is a person who we all know and love, which is Alexander the Great. He's a Greek. He's actually the son of, I think it was King Philip, and he's out of this Athens area, the city-state that is conquering. And what happened was that King Philip was held hostage for a while, and then he was assassinated. And so Alexander didn't take too kindly for that, and so he comes back with a vengeance. What we know about Alexander is he's actually from Greece, and he was tutored by Aristotle. If we remember, last week or one of the last videos, we had SPA, right? So Socrates, Plato, Aristotle. So Aristotle is the most recent, let's say, of the philosophers. So he had kind of a classic Greek training from Aristotle. And what he does is he comes over and he liberates part of Egypt, and they make him one of the pharaohs. Pharaoh of Egypt. Now, it didn't last long, but it lasted long enough for him to set up this city, and of course he names it after himself, because who wouldn't? You're the conqueror. And it happens to be still today named Alexandria. So interestingly, this is a center for trade. It's a hub for the Mediterranean. because it's also at the mouth of the Nile, so you can ship things down the river. So it's actually a really well-located city for them. And what happens is, until the time of Ptolemy, who's the next big pharaoh for Egypt, the next ruler, Alexander is the one who's considered their leader. So this connects Egypt to Greece in a very real way. All right, so we've got this kind of thing going on. Some things that Alexandria is known for. There are two big things that they're known for. One is, and I know it's so interesting, they had a school, it was called the Museum. Okay, and we'll talk a little bit about that today. The Museum, so very, descriptive school. It was based on Plato's Academy because, of course, Alexander was one of Aristotle's students. So it goes back to the classic Greek thing. They wanted to preserve and promote knowledge. They were said to have the best library in the ancient world, and in true, Greek fashion, they called it the library. I know. It's sad. So these are the two things that is really well known for, Alexandria is. And there's some literature, more modern literature, that talks about when Alexandria was burning and when the library was burning and things like that, which we'll talk about a little bit later, how that comes about happening. It's almost always in war. But for now, we'll just say those are the two things that they were known for. The museum, what the museum was known for was, it was one of the first examples that we have where scholars were asked to come, and they were paid, they were given food, and they were given housing. So it's kind of a nice thing because, yeah, you're just a scholar. Maybe you're trying to learn, the new science of medicine. Maybe you're trying to do some research or experiment with medicine. Maybe you're trying to learn math, those kinds of things. But not only are we going to feed and house you, but we'll give you a little bit of money too. So this is your opportunity to actually, make some cash. So that's interesting. And then what happens is, because you're working for the pharaoh, because you're working for a patron, you're expected to actually produce. So if I'm your king and I'm paying you and I'm housing you and I'm feeding you, then I want you to make me look good. So you had better be producing. You better figure out something math-wise that nobody else knows. You better figure out which bone is attached to which bone in the human body. You better do something that makes me look good, because I am supporting you wholeheartedly. So it's a new concept, but because of this royal patronage thing, it actually becomes a big thing as we head into like medieval times and stuff like that. You're really expected to put out lots of service for the king. But the nice thing is that because he's paying, because he's feeding, people just flock to the area. They really want to be a part of this. The library, it's really an extensive library. And depending on what time period you look at, there were housed in it anywhere from 300,000 to 700,000 texts, scrolls, and books. So just basic documents in there, 300,000 to 700,000 of those. And that is a huge library, even by today's standards, but specifically for ancient times. Really, really big. Okay, so that's what they're known for. One of their most popular mathematicians, everybody knows this name, is Euclid. I think most of us know this name, maybe not everybody. But Euclid is a very popular mathematician. He comes out of this area. He studied at the museum. His dates are 323 to 285 BC. It's We're getting closer to the time of Christ. Okay, only 300 years before now. The thing that he's known the most for that people talk about is his geometry, Euclidean geometry. So he wrote the books, The Elements. And I say the books because this was actually, we call it a book nowadays, but it was actually 13 volumes. I think there are only like 9 of them surviving, maybe 8. So between burnings and this and that and moving and stuff, we've lost some of his volumes. We do have a huge chunk of them, so we know that he studied all kinds of stuff inside of his elements. It wasn't just geometry, there was other stuff, but in particular, he's really well known for laying out definitions of geometry. Putting together axioms, being able to use logic. And it said that aside from the Bible, the book or books, The Elements, is the most read book ever. So even today, right behind the Bible, most read after the Bible. So that's a lot of people reading The Elements, which is really interesting. It means, it lets you know that it stands the test of time, so to speak, right? Because we're still talking well over 2,000 years ago, and he must have had a lot of really good logic. They say that Euclid had the ability, if you wanted to prove something like, say, okay, you've got a semicircle and you inscribe an angle in there, is it a right angle or is it not a right angle? If you wanted to prove that, they say that Euclid could just kind of look at that and say, well, okay, if I'm going to do that, I need this axiom, this definition, and that postulate. And just stick it all together and boom, there's his theory, there's his proof. So he could just come up with those off the top of his head, whereas a lot of people couldn't do that. So, oops, this is not the right picture. Why am I drawing that? Here, there. There's my picture. Sorry. I had put my angle on the wrong side of my semicircle. All right, so, but that's what they said. He could just look at it and put it together and boom, he's got it. And whereas a lot of people might even look at a theorem and go, oh, I don't know where to start to prove that. But he just had a knack for it. Okay. One of his famous quotes is supposedly there was a student who said, he's giving a lecture in whatever math, and the student says, well, teacher, you know, basically the old argument that we get today, so they were doing it thousands of years ago, why should I study this? What will I get for learning it? Okay, so nowadays we say, why would I bother? How does it help me? So what he said was, someone give that man a coin if he must profit from what he learns. So I would say, well, it's good for you. Or, you know, oh, it'll help you out in your future once you're a math teacher or once you're this or once you're that. But he was just like, well, if you must profit from what I'm about to teach you, then here, let's give him a coin so that he'll shut up and let us do what we want to talk about. He had a book called The Propositions. Inside of it, he was very good at combining geometry and algebra. And one of his major areas, and this is what we're going to look at now, is number theory. So he's not really well known for number theory, but like he's more known for his Euclidean geometry. But he actually did a lot of stuff in number theory. And in fact, there's stories about that Euclid was heads and shoulders above all the other people at the museum, and he was such a good scholar, I guess you would say, and produced so much that there was nobody else in his time that was as prolific of a writer and that got as much stuff accomplished in math at this point in math history. So his number theory, one of the big things that he did, that he gives us, so this is his contribution to us, to modern day, is the notation that looks like this. A with a straight line B. So if you've taken a number theory class or some other classes, you may have seen this notation. And usually we read that A divides B, or you would say A goes evenly into B, or A is a factor of B, or B is divisible by A. So there's lots of ways people say it. But that particular notation, we can attribute it to Euclid. And maybe even, I think, more important is he gives us this notation. With same notation, but with a little slash through it. And so, of course, that means A does not divide B, right? So it's actually quite a genius little notation there. We use it all the time nowadays, not just in math. You might go to, I don't know, you might go, oh, I'm a terrible artist. You might see something like this with a little person, and it'll have a slash through it, right? Don't do that, don't walk. Or you might see one of those signs, and it has a cigarette on it. I know, terrible artist. Smoke, that's smoke coming up. Okay, so it's a smoking sign, but then there's a slash through it, no smoking. You know, so we actually use that all the time, that little slash, and we know that it means don't do that. Whatever this is that I'm telling you, here it's A divides B, here it's A does not divide B. And it actually permeates all over our culture, not just in the math, but in particular in the math. If we want something to be equal, okay, we use an equal sign. If we want not equal, we just put the slash through it. And we're pretty sure we can take that notation back to Euclid. So that's kind of nice of him to help us out that way. So one of his areas that he looked at was common divisors. So numbers that will evenly divide two different numbers, two or more different numbers. So for instance, one of the things that we can do nowadays, and we can do it pretty easily, is we can talk about the GCD, greatest common divisor in this case, not denominator. I know sometimes in math we recycle. So, okay. GCD of 30, 48 equals, and nowadays there's lots of ways to do this particular problem. You can list out the prime factorization of both of them and see what they have in common. You can list out all the factors of either one. So it might look like you're over here doing a factor tree or something. 6 times 5, 2 times 3, and then 48 would be 6 times 8. Oh, I'm going to cheat and do 2 times 2 times 2 and 2 times 3. So you can do a prime factorization tree or a factor tree, or you could just list out all the things that go evenly into them. And sooner or later, what you're going to have is you're going to say, hey, look, they're both divisible by 2 times 3. So they're both divisible by 6. And that's the largest number that's divisible that divides evenly into both of them, because this one has a 5 and the other one doesn't. This one has 3 2s and that one doesn't. So 6 is my GCD. And we have lots of ways to do those kinds of things nowadays. Sometimes they can be a little tricky with bigger numbers. So we might founder a while looking for, like, I don't know, if I had 732 or something like that. It might take me a while to come up with all my factors. So, but we got some pretty good methods. But what we know is that Euclid came up with an algorithm. So it's called the Euclidean Algorithm. I know. Just like Euclidean geometry gets his name. However, we think he actually earned that as opposed to Pythagoras, who just got his name on something he didn't actually come up with. Okay. So the Euclidean algorithm, and what it does is it finds a GCD by using this little process that he had. What he said is, if you want to find GCD of A comma B, then you can set up an equation that looks like A equals B times, and he's going to have a couple of little letters in here. Q sub 1, where Q sub 1 or Qi, whichever one you want to talk about, is a quotient, plus r sub I think it is an I. Let me look. Let me cheat real fast and look at my notes. I'm not even on the right page. Yep, i's. Okay. Q sub I plus r sub I, where Q is the quotient and r is the remainder. So what he says is, look, you pick the biggest of these numbers. If you always use the bigger of the numbers as A, then we'll always come up with the same exact answer no matter what we did. So in this case, we're going to do this one that we already know the answer to. We're going to cheat because we know the answer already. But we're going to say 48 equals. And the B here would be the smaller of the two numbers, which is 30. Times something. We don't know what that quotient is going to be. But quotient literally means you're dividing into, right? Okay, the answer after I've divided into something. And then the r is going to be a remainder. So I like to put parentheses around the quotient and box around the remainder just so I can keep things straight. If you don't like doing it that way, then do it however you want. It's fine. Okay, but what he would say is, look, 30 goes into 48 one time. Okay, that's my quotient. The remainder would be 18. Okay. And so he's like, I'm looking for the remainder of 0 because if I get a 0, I know I had something that went in evenly because there's no leftovers. So that didn't work. So we're going to rearrange this just slightly. We're going to move the 30. It's now the biggest number, right? 30 is bigger than 18. So I'm going to move the 30 into the 48 slot, and I'm going to move the 18 into the 30 slot. And we'll do it again. So we just do this kind of as an iterative process over and over and over again until finally at some point I'm going to end up with a 0 for my remainder. Okay, so 18 goes into 30 one time. I get a leftover of 12. Again, that's not a 0, so I do it again. So now I have a new little equation. 18 looks like 12 times something plus something. Well, 12 goes into 18 one time. The remainder is a 6. And now I'm feeling good because we know the answer is 6, so I'm on the right track. So I do it one more time because I'm looking for a remainder of 0. 12 is 6 times something plus something. So sure enough, 6 goes into 12 twice, nice and even with a remainder of 0. Okay. So what Euclid said was that if you can set something up in this particular format and then work off of the remainders until I get a remainder of 0, then the remainder directly before the 0 is the greatest common divisor. And the reason is because it's the one that went into this remainder. And that was the leftovers after I pulled that one out. So I'm just always working with these remainders and trying to figure out what will go evenly into the leftovers so that I can see, okay, if it goes into the leftovers and then the remainder before went in, then I'm okay. So this is going to divide in. So this is going to be my GCD for 48 and 30. So once I get that 0, I go to the line before it, and whatever that remainder is, there's my GCD, greatest common divisor, which we knew. We knew it was 6. But we also have some pretty nice tools available to us now that he didn't necessarily have. So for him to be thinking in this method 300 years before Christ is pretty impressive, actually. It's pretty advanced thinking. All right. So what I'm going to do is I'm going to give you an example, let you work on it real quickly. If you're watching the video, then you can pause it if you would like. That'll be great. And we are going to do, oh, there's my thing. I want you to use the Euclidean algorithm. An algorithm just means a way of doing things, right? Use the Euclidean algorithm to find the GCD for 220 and 96. Now that's one I can't do off the top of my head. So play with that one for a second, see what you get. Put the video on pause if you must. Work it out. You'll be all right. Okay, so I've got my work up here. It took me 4 steps to get there. The last one also took 4 steps. It doesn't always take 4 steps. I'll show you one in a second that does not take 4 steps. In fact, it'll take us very few steps. But now I look at it and I say the GCD must be 4. All right, so I've got it. There it is. And yeah, I could have factored them out and done stuff, but that's kind of cool that it works. So if you want to check it, you can list out all the factors or do the factor tree, or you could even use a Venn diagram and figure it out. There's lots of methods nowadays for finding GCDs. All right, so here's a weird one. Let's do the same thing, and I just want you to think about it real quickly. I want you to do the GCD for 48 and 24. So hopefully that comes to us pretty quickly. 24 actually divides into 48. So this is a really weird situation where one of the two numbers is actually the GCD. So it's going to be 24, right? That's kind of weird. But if we use Euclid's way of doing it, it actually comes to a head very quickly, which is kind of interesting because we see it right here in one step, right? So he's got a very nice way, if we're using that equation, that it says, okay, 24 times 2, remainder is 0. And you go, wait a minute, so what is it? And the answer is it's the number that you actually used to divide into it. So if one of the numbers is a factor of the other one, then you're not going to be able to go to the line previously above it, right? Like we did before. So you'll just have to know, oh, that means that this guy is my GCD. No worries. So it's kind of an unusual case. Things happen. You could also have something where they don't have any common factors other than 1. And in that case, you would follow the process all the way down, and you'd have a 1 at the end, and you'd be like, dang it. Okay, so like, it wouldn't be too bad if it was 4 and 5, because those are relatively small too, but we could see, yeah, it's not going to work. Well, you get 1, it's just a 1. Okay, so that's kind of the idea there. Now, interestingly, what they want to do, there's actually a 2-part piece to this Euclidean algorithm, and on a test, I have a tendency to give it as 2 separate questions. So one might be, find the GCD between 220 and 96, and that's one question. And then on the same page, so it takes up a lot of space too, but maybe halfway down, I'll give another question, and it's related to this one, and I'll say something like, using your GCD from the previous problem, so hopefully you got the right answer there. If you're working off of an incorrect answer, it's okay. I'll follow you down that rabbit hole and see if your math's right for the rest of the problem, but it kind of stinks to start out with the wrong answer to begin with. But using your GCD from up here, now what Euclid would do is he would want to write an equation that looks like this. The GCD between the two numbers is equal to, and the way that your book usually uses it says something like AX plus BY. Okay. And the thing is, there are actually lots of ways, for instance, that I can write 220, some multiple of 220 and some multiple of 96, and I can combine those and I can get a 4, right? Because this is actually a linear equation, right? So I can have different things to do it. But if I use the Euclidean way of doing things, we're only going to get the one GCD. There's only one answer there. And then if I use it here in the way we're about to show it, then we're only going to get one answer also. So we're not necessarily doing weird multiples or combinations of these. We're looking for the one that Euclid would come up with first. So here's what he did. He said, hey, look, what we're trying to say is that 4, we're going to use the one we just did. 4 is some combination of 220 times a number plus some combination of 96 times a number. That's what he wants. He wants us to find that equation. Find x and y, basically, is what we're after. Okay? Now, the problem that comes to my mind immediately is that if I take 220 and times some multiple of 220 and add to it some other multiple of 96, I'm already above 4, right? And I'm trying to make a combination that equals 4. So one of those numbers is going to have to be negative in order to counterbalance and bring it back down, compensate back down to a 4. So we're going to have to look at that. Sometimes some books will have a minus sign here, but I notice in y'all's book it pretty much always has a plus sign. So we're going to end up making one of them a negative number. So here's how it goes. This is Webster Brain. Again, on a test, you're going to have to at least show me enough work that shows me that you understand the process that Euclid was using. But if you skip some of my steps, then I'll forgive you. Okay, as long as your math's right, you get to the right answer. But you still need to show me something that lets me know what you did. So, for instance, what Euclid's going to do is he's going to say, look, I'm trying to write 4, in this case, whatever the GCD is, 4 as some combination of these other things. Well, if I come back up here to what I considered the GCD equation, which is right here, I don't need this 0 guy, right? That was just telling me, hey, you found it. Okay, so I don't need him. But if I come back up to this equation, then I've kind of got a little equation already sitting there with a 4 in it. I'm going to rearrange it so the 4 is by itself on the equal sign, because I know that's what I'm after here. So 4 equals, and I'm just going to subtract this 12 times 2 over 28 minus 12 times 2. And I'll caution you, some mistakes I've seen students do here is a lot of times they want to say, well, I'll just make that 24. 28 minus 24, right? Because we know 28 minus 24 is 4, so yay. But the problem is that what I'm about to do is I'm going to work up using all of these remainder equations that we had before. And so we're going to solve all of these for just the remainder, like I just solved the 4, this bottom one for the 4. So we're going to solve all of those, and so in a minute I'm going to have an equation here that's solved for 12. So because I have 12, I want this equation to still have the 12 in it, because that's the number that I have up here. I don't want it to be 24 because then it doesn't match up. So, and I'm going to be doing some substitution. So it's going to end up really good if instead of multiplying things out, you actually count them as groups of blah, whatever those groups are. Okay, so here we go. I've got that equation. I'm just going to come out here beside here and write them. For this 12 guy, if I solved for 12, I would have 12 equals 96 minus 28 times 3, or you could think 3 groups of 28. And that's literally what we did. We took the 96, we pulled out 3 groups of 28, and when we were finished, we had 12 as a leftover, right? Okay, and the same thing on the one before that. I've got a 28, because that was my remainder, is equal to 220 minus 96 times 2. Okay, so I've used this equation, I've used this equation, I've used this equation. So I think we're good. We've got them all rewritten. And then what we're looking for, if you keep in mind where you're headed for, we want some equation that has 2 20s and 96s in it. We don't want 28s and 12s, right? So what we'd like to do is come up here to these 2 equations that we've just rewritten and rearrange or substitute them in. I'm going to get rid of these so I don't. Sometimes this just gets a little hectic with all the writing that you're doing. So I'm going to substitute these in, and whatever the 12 says it's equal to here, I'm going to plug that in here for the 12. Sometimes people try to go ahead and substitute for the 28 also. You can do that, but the problem is here, whenever I substitute for the 12, I'm going to have a 28 again, so you're going to have to back substitute again. So I just only want to substitute for the 28 once. So that's the way I do it. If you want to skip some steps, it's fine. Okay. So what I'm doing is I'm rewriting that equation. The 4 equals, this is my GCD, right? GCD of 220 and 96. Rewriting that GCD equation, but I know I'm going to substitute out for the 12, so I just put parentheses there for the 12. And I'm going to cheat, and wherever I see a 12, I'm going to put in this stuff right here. So instead of my 12, I'm going to mark that out. I'm going to put 220, oh, sorry, I just lied. 96 minus 28 times 3. I was looking at the wrong equation. I even circled it, dang it. Now this bugs people a little bit, so if it bugs you, you might think to yourself, look, this is just distribution, right? I've got a negative in the front, I've got a 2 in the back. Take that 2 and move him to the front, because I'm going to distribute both of those through. So it's really like a negative 2 going in there. But remember that that's negative 2 groups, and don't multiply, actually treat it like groups. So 4 equals 28 minus, and it's going to be 2 groups of 96, 96 times 2, and then a negative and a negative. It's going to be a positive. And here's where people get confused a little bit. It was 28, and the question is, this is number of groups 2 times number of groups 3, so 2 times 3 is 6 whole groups of 28. Sometimes I see people and they'll try to add that. So it's not tough math. The math is actually really easy. It's add, subtract, multiply, divide math, right? It's arithmetic. It's just keeping up with all the details and watching out for your negatives, making sure you substituted the right thing, that kind of stuff. All right, so I've got that guy. Yay. Now I see, hey, I got a couple of like terms here. So I've got 1 group of 28s over here, and I've got 6 groups of 28s over there. So in Webster Brain, I have 7 groups of 28s, right? 1 plus 6 is 7 groups. If you don't like the minus sign sitting in front of the 96, you can put it in with the negative 2. I like it sitting in front of the 96. If you don't like the negative in the front, then you can move that to the back. I just don't care. So I'm not going to be picky about the way that your writing looks here. I do have a 96. That's good. The problem is I have this 28 that I'd like to get rid of. So I'm going to substitute for him now. I only have one equation left up here. And thankfully, it is the 28 equation, which I need. I'll figure out what's going in there for that 28. So where I see a 28, I'm going to substitute 220. I'll move it up in a second. Minus 96 times 2. Because that's what's in this equation. Put it in there. So if you're watching on the video, you can back it up and rewind and pause and all kinds of stuff so that you can see exactly what I did there. If you still have questions, then shoot me an email or come see me. Now I've got just a 7 that I'm multiplying through. That's not so bad. Negative 96 times 2 plus. Again, I'm going to distribute, and I'm going to keep it as groups. So I've got 7 groups of 220 minus 96 times, and again, it was 2 groups, and now I'm multiplying that by 7 groups, so it's 14 groups. Okay. So now I'm looking and I'm saying, hey, wait a minute. That's a negative 2 groups, and that's a negative 14 groups, so this is kind of interesting because I've got a negative 16 groups. Let me rearrange this just a little bit. 220 times 7 minus 96 times 16. It's a negative 2 and a negative 14, so those are negative 16 groups. So I'm getting there. What I wanted was, did I write it down? Oh, there it is. I wanted something that looked like this with a plus sign in front. And I've almost got that, but I've got the negative sign in front. So if you want it to absolutely look like that, you need to distribute that negative into it. So what we really have here is, if this is my x and this is my y, x equals 7, y equals negative 16. So again, it's just a matter of keeping up with your negatives and paying attention. So yay. And that is how it'll pull it back down, right? The 220 times 7 is going to be a really large number. But we're going to say, hey, but we're using 96 times negative 16. That's going to pull it back down, and that's how it'll equal out to be a 4. So one of them's got to be negative in there somewhere. Dang it. So what I'd like for you to do is go ahead and work on for yourself so you can see it. The GCD for 30 and 48, which we did a minute ago, we said that that was 4. Don't have it with me. I'll have to work it out if you want to see it. No, it was 6. I'm sorry. The GCD of 30 and 48 was 6. So go ahead and work that out and see if you can come up with what the x and the y would be if you wrote 6 equals 48 times x plus 30 times y. See if you can figure out what the x and the y would be there, because we already worked on those a little bit, so you can see it. All right. If you need some practice problems, I have a couple. You can do the GCD of 45 and 75. That one's interesting. You can do the GCD. This one is a little bit more work, but it will let you know for sure. 30,504 and 744. This one, I'll tell you the answer is 24. Okay, so it's kind of a big number. So you can do that and rearrange it and find your x and your y if you'd like to. All right, there we go. Okay, yes. So that's the Euclidean algorithm. I can see you having some homework on that, so make sure you feel comfortable with it and you can do it. We're not quite done with these guys, so we're going to wrap up a little bit more about Euclid, and then we'll probably call it a day for the notes, so yay. Okay. Dun, dun, dun. We talked a little bit about Euclid. One thing I want to talk about that he did, it was actually one of his focal points, and I'm not going to do the entire proof. What I'm going to do is I cheated and printed it out. And so I'll show it now, and then I'm going to put it on the D2L site so that you can look at it if you want to. He was obsessed for a while with constructing regular polygons. So a regular polygon is one, let's try the smallest possible. The smallest possible polygon is a 3-sided polygon, right? A triangle. And so a regular polygon is one that has congruent sides. And therefore, because its sides are congruent, also its angles are congruent. Now, we could have a quadrilateral with congruent sides that doesn't have congruent angles, so you have to watch out a little bit. There's a rhombus, right, that's out there. But that guy is not the regular guy. So this equilateral triangle would be my regular triangle. My regular quadrilateral would not be the rhombus. It would be the square. Okay. And those two are actually relatively easy to construct. And pretty much the reason for that is because when you're constructing, you're just going to take this leg length and duplicate it. So, and I need to be able to rotate this 60 degrees, right? Because 180 degrees inside of a triangle. So I rotate it 60 degrees. Well, 60 degrees is pretty easy to get to because you can either take 180 degrees and divide it by 3, or you can take 360 and divide it by 6. But we can construct a 60-degree angle pretty easily, so that's not bad. So you do one side, you construct a 60-degree angle, you do another side, 60 degrees, another side. And it works out pretty easily. Similarly, with a square, I just need the first side length, and then if this was a straight line, it would be 180. So I make a perpendicular, which would be here, and then I duplicate this length over here. Okay, so it's actually really easy to make a perpendicular in constructions, and then I just do it again. Make it perpendicular, duplicate, make it perpendicular, duplicate. Duplicate just meaning that you copy that side length over, so that means it's congruent. So the square is pretty easy, the equilateral is pretty easy, but the one that was bugging him, and I apologize in advance, I'm not an artist, but I will do my darndest, is the pentagon. So the pentagon is actually not quite a house. I think that that's where people mess up They try to make it look like a house. Hey, that one's not too terribly bad. So instead, it's like a house, but the bottom is kind of leaning in a little bit. But all 5 of these sides need to be congruent. So if I'm trying to use the same technique that I used for the triangle and the square, then what I would do is I'd figure out how many degrees are in here inside of my pentagon. And so this is the pentagon. And I would try to duplicate those out. The problem is that this guy, the triangle had 180 degrees. The square had 360 degrees. And there's a lovely pattern that says you just add 180 every time when you add a side. You add 180 degrees inside on these interior angles here. So this pentagon would be 540 degrees. Okay. Well, I can take 360 and divide that by 4. That's 90. It's easy to make a 90. I can take 180 divided by 3. That's 60. It's easy to make that. But when I take 540 degrees and I divide that by 5, that's 108 degrees. And 108 degrees, not so easy to construct, right? So, and it's not any, like you can't use 180 and divide it by something to get right there to 108. So this is not a pretty angle to try to construct. And so, ancient Greeks were having a problem making this guy happen. They knew he should be able to happen. They were just having an issue. So Euclid is, as far as we know, the first one who thought, okay, hang on. If I can't do these angles, maybe I should look at what's called the central angles. So the central angles actually start at the center of the whatever polygon we're doing and radiate out to the vertices. Similar to if I had a circle, I would have a radius. So I'd have these things coming out to the vertices. And he said, hang on. So inside of here, if I go around this center point, is 360 degrees because that's a circle. Okay. So if I take the 360 degrees and I divide it by 5, well, that should be 72 degrees. Still not a pretty number. Okay. But if I can figure out how to do 72 degrees, then I can construct this angle, make a side, and then I can duplicate that angle, 72, 72, 72, 72, and then all I'll have to do is connect the dots, so to speak, from here to here, from here to here, from here to here. So then it would become relatively easy. So he came up with a way for him to basically, one of the things he does, and I'm not going to get into the entire construction, but basically what he does is he figures out how to make a 144 degree angle. And if I can cut that in half, I'll make 72. And he does a lot of, it's actually 3 pages worth of notes if we had time to go through it, but we lost some time, and this is a good spot for me to cut. So he figures out how can I construct this, and he actually does kind of some algebra. He combines the geometry with the algebra, and he has a proportion going on. So I'll cheat and show you. That's why I brought it, and then I'll put it online. So this is the picture of his original pentagon. Yay. You can see it looks very pretty. Okay. But basically what he does right in here, it's not quite a rhombus, but right in here is he says, if I can figure out how to do 144 degrees, there's a lot of construction going on in there, then what I've got here is a triangle whose base angles are 72 degrees. I can have 72, 72, and then the other one would be what? 37, I think. No, that's not right. Whatever the other one would be, 36. Yeah, it's like I'm getting close. And then he sees that 36 is half of 72. So he sees some special relationships going in there, and he says, hey, let me construct this guy. If I can just construct this guy, he's an isosceles triangle, then maybe I can use that. So he does a lot of stuff. There's a lot of similar triangles and things like that going on. Here's the lovely picture with similar triangles. So we can see that. You can look at this. I've got it loaded into the D2L, and you can play with it. But he does that, and then he says, hey, look, I can do this, and one of the calculations, so this is where it gets important, one of his calculations uses this number. And as far as we know, it's one of the first times that we've had to do this. So, does he use the plus or minus? So basically he sets up a distance formula kind of thing, and he ends up with 1 plus or minus the square root of 5 with a quadratic, it's actually a quadratic formula, over 2. Now he's only going to use the plus guy, but if we were solving a quadratic, we would have both the plus and the minus. So because he only uses the plus guy, what happens is this gives us 1 plus the square root of 5 over 2. Do you recognize that? It's just a number that's in your head somewhere, right? No. It's about 1.618 as a decimal. And this guy is called the golden ratio. Okay, or phi, right? So we see him later. He pops up all over mathematics, Fibonacci spirals and things like that. So it's the golden ratio. Leonardo da Vinci studied the golden ratio in the human body. We see it in music. It's all over the place. So if you haven't thought about the golden ratio yet, you might go look up the golden ratio, because I can almost guarantee you there will be a question about what is the golden ratio on the test. And basically what it's believed is that this is, in nature, this is a naturally occurring relationship, this ratio, that is pleasing to the human eye. Okay, this is the way that a lot of people, like Leonardo da Vinci, would have called it pleasing to the human eye. So, for instance, if you're looking at the face, I know, not an artist, and there's my face. You measure the distance from the outside of the eye to the outside of the eye, like temple to temple, and then compare that, the distance from, I think it's the forehead to the nose, then do a ratio on it. The relationship for what we would consider classically beautiful people is approximately 1.6. Okay? If you, for instance, have a really long face, then your ratio will be out of sync, right? So if your eyes are close together but your nose is way down here, then sad day for you. You're not as classically beautiful because you're not as balanced as these other people. So your ratio is all out of whack. Maybe it's closer to, I don't know, 2. So that's what goes on. And actually, we see it in things like picture frames. So if you look at the picture frames that are most people like, you're probably going to be somewhere around, say, an 8 by 10, okay, which is like a 1.4, is that right? 1.2, okay, versus a 3 by 5, which is going to give you actually 1.6, I think it is. So 3 by 5s, people like those. 4 by 6s, people like those. But if I gave you a really long, tall, skinny picture frame, you'd be like, what am I supposed to do with this? You know, unless you have, I don't know, a waterfall or something. But inside of people's faces and human bodies and things like that, the ratios that are closest to 1.68, those are the ones that we want. We'll actually see it in one of our sequences later, too. So it's kind of interesting. So that's his big contribution. He's already looking at one of the triangles. This comes, by the way, from some triangles. You can see 1, 2, square root of 5. So you can see it coming in there. And you're just using Pythagorean theorem, right? 1 squared, 2 squared, 5. Take the square root of 5. So there you go. So you'll see it pop up, and that's actually kind of an interesting development. And he had it 300 years before Christ. So this number, we'll see him all throughout the semester. As we look toward the next project that you guys are going to do, hopefully maybe somebody will look into the golden ratio, and it'll be kind of cool. Because there's a lot of information out there about it. It's just I don't have tons and tons of time. When I see it in the curriculum, it pops up, I'll mention it, but I'm not going to do a whole class on golden ratio. So I think that's about it for Euclid. We have 1 or 2 more people to go. I'm going to put a video into the D2L so that everybody can look at it to prepare for our next mathematician, who is Archimedes. Yay. Who's considered one of the greatest mathematicians of all time. And there's a really cool, it's a NOVA, N-O-V-A, NOVA video that talks about some of the really interesting stuff about Archimedes. So I'm going to stick that up online and maybe some homework, and that's it. And we'll be done with Greeks next time. Yay. All right, thanks. Have a good night.